Welcome to the course on Biostatistics and Design of Experiments. We will continue on the topic of non-parametric test. Yesterday I talked about non-parametric test, and generally this non-parametric test is used when the data is ordinal. That means we do not have a x axis, like for example changes in a parameter as a function of time or and so on actually. So it is more of ordinal, it is numbers. The next one is if the distribution does not follow say a normal distribution, okay, or a chi-square distribution or a f distribution or a t distribution, okay. If the variances are unequal, okay, so all these conditions we cannot use the parametric test. We have spent a lot of time on these parametric tests like your f test, t test, and chi-square test, z test and so on. So, we cannot use any one of these, and we need to resort to non-parametric test. So, what are those non-parametric tests? We have these on equivalent to a 2 sample t test. If you are comparing 2 independent samples, there is something called Mann-Whitney-Wilcoxon rank sum test. Then if you are doing a pair t test, that means you are using the same subjects for say control and test, that is comparing dependent variables. There is something called sign test or Wilcoxon sign rank test. If you are doing a one way ANOVA equivalent, that is you are comparing independent samples, then there is something called Kruskal-Wallis test. Okay. So, yesterday in the previous class we looked at these two rank sum test, sign test and sign rank test and so on. Now, let us look at equivalent to your one way ANOVA. What do we do in one way ANOVA? We have several sets of samples and we are trying to compare them. If you have the homogeneity of variance, we can use ANOVA, but otherwise then we need to resort to something called a Kruskal-Wallis test. So, if you want to compare 3 or more populations, if you have 2 or more 2 population, then of course we can use this Mann-Whitney-Wilcoxon rank sum test, or if it is a paired then we can use the sign test and so on. But if we are having 3 or more populations, then we resort to something called Kruskal-Wallis test. So, because one way ANOVA generally assumes normality or equality of variance or homogeneity of variance, so in a non-parametric situation we use this particular test. So, what does it do? So, it looks at all the observations and then ranks them, okay, and then once it ranks them we will sum up each of the group ranks, okay. So, you understand. So, we will sum up each of the group ranks and we will get say some summation R1, R2, R3, okay. So, if some of these R's are larger than others, then it indicates the response values in different groups come from different populations, okay. So, that is what it is. So, what we do is we put all the data together, we rank them in an ascending order, and then for each group we sum up all the ranks, and then we compare these ranks using some statistic, okay. Let us look at a problem. So, before that, this is the test statistic. So, 12 divided by n into n plus 1, where n is the total sample size. So, if we have say many groups, each one having n1, n2, nk sample size, we add up all, that gives you n. And then here you have a summation I is equal to 1 to k, ni, that is the number of samples in that ith data set, okay. Ri by ni is the average rank for group I minus n plus 1 divided by 2, okay. This is the test statistics. So, what we do under the null hypothesis, this is an approximate chi-square distribution with degrees of freedom equal to k minus 1, that is the approximation is okay when each group contains at least 5 observations, okay. So, we compare this test statistics, okay, using the chi-square distribution. Okay, let us look at an example. This example was taken up from this particular paper, okay. It is called clinical therapeutics. So, a clinical trial evaluating the fever reducing effect of 3 drugs are tested: aspirin, ibuprofen, acetaminophen, okay. So, it was given to adults and they were tested when they had a body temperature of 100 to 100.9 Okay. The subjects were randomly given either aspirin or ibuprofen or acetaminophen, and after 2 hours their body temperature was again recorded, okay, and then it is listed. So, 3 drugs, so it is very random set of data. So, the temperature decrease is shown here. Of course, in this particular case there is a temperature increase. So, aspirin we had 4 candidates, they had a temperature decrease of these numbers. Ibuprofen there are 5 candidates who had a temperature decrease of these, and acetaminophen we had 6 candidates, 5 of them temperature decreased, 1 case temperature also increased. Now, we add up all these and then rank them. We start the smallest with rank 1 and then go upwards. Okay. So, when you do that, so this is the 1 because this is the smallest number. Okay, then comes 2, then 3, 4, 5, like that you go again, go on. Finally, we end up with 15. Okay. Now, what do? We add up all these ranks together, these ranks together, these ranks together. So, the total data set is 15, 4 plus 5, 9 plus 6, 15. So, capital N is 15. If you look at RIs, that means the summation, if you add up all these, okay, you get 44, total number of data points is 4, if you add up all these you get 50, total number of data points is 5, you add up all these 6, total is 26. So, obviously there seems to be some large difference. So, you may expect it to be behaving differently. Now, we go to the test statistic, okay. H is equal to, you remember this test statistics which I introduced. So, 12 divided by 15 plus 16, 3 terms are coming 4, 5, 6 because we have 3 sets of data 4, 5, 6 here, okay. 4, 5, 6, and then 44 is the sum for data set 1, 50 the sum for data set 2, 26 is the sum of data set 3. So, 4, 5, 6 is the terms that is coming in denominator. So, we do this addition, we end up with 6.833. Okay. So, you look at the chi-square test for 6.833. So, the area comes out to be 0.03. So, obviously it is significant. So, you reject the null hypothesis, or you look at the chi-square table for this is a 3 data sets are there, okay, acetaminophen, ibuprofen and aspirin. So, the degrees of freedom is 2. So, we can look into this, you remember this table, we look into the 2. For a 95% one sided we get 5.99, and the H the statistic comes to be 6.833. So, we reject the null hypothesis at 95% confidence for one tail. Okay. This is how you do this. So, what we do is we combine all the data, we rank them and then add up each one of the set of ranks separately, and then we use this formula. This is the statistic, 12 divided by the total number of data points capital N, this is the sum of the ranks for each I, okay, sum of the rank for each I divided by Ni, that is the total number of points in that set minus N is the total plus 1 divided by 2, and then you compare it with the chi-square table. Okay, now the next question is which drug is statistically significantly different from the other. Now, again there is a different type of approach, okay, again there is a different types. So, the conclusion, using the Kruskal-Wallis test, we have evidence to suggest that the temperature changes after taking different drugs are not the same, because P comes out to be 0.033 area. We can get it using Excel. So, Excel has this command called chi-dist. So, we can put this chi-dist, I had explained this command. So, chi-dist we get 6.833 comma 2 degrees of freedom, okay, it gives you 0.03287, that is the probability, or that is the area under this curve. Okay. So, we can use either the command chi-dist from Excel and get the probability value, or we can use this table, okay, or we can use this table for 0.05 one sided, 2 degrees of freedom 5.99, and you can say this statistics calculated is larger than 5.99, okay. So we reject the null hypothesis. Is there a statistically significant difference between these 3 drugs? How do you go about doing that? There is another test, okay, which drugs significantly differ from one another. There is something called multiple comparisons for Kruskal-Wallis test. Okay, so from the Kruskal-Wallis test we concluded, okay, there is a statistically significant difference between these 3 drugs. Okay, and now how do you find out which drug is statistically different? So to determine that, there is another formula like this. If group I is significantly different from group J, that means if you take one drug, say aspirin, and then you call this ibuprofen, so you put in the aspirin data, put in the ibuprofen data, okay, this is the number, this is the total, and then this is the total 15 is this number, and then compute p value and compare to alpha divided by 2m, where m is the number of possible pairwise comparison, that is m is given by k multiplied by k minus 1 by 2. So you need to compare this results, okay, with this particular m value and see whether this result is less than this value. Okay. So what is k? Let us look into this problem. So the statistics, so let us compare aspirin and acetaminophen. So Ri minus Rj, here you have Ni, you have Nj, then N here Ni Nj. As you know, for okay, for aspirin Ni is 4, for acetaminophen Nj is 6, okay, and then the total N is 15. So we substitute all these into this, okay. Okay, we get the Z, that is, once you calculate the Z, the probability of 0.0104 is obtained from your Z table, okay, and then okay, then we compare it, then we look at it 0.0, okay, then we look at 0.05 divided by 2.3, that is k, that is alpha is 0.05 divided by 2m, where 2m is given by k into k minus 1 divided by 2, okay, k is k, so you get this as 0.00833, okay, 0.00833, okay, and this is much less than this particular probability value, okay. So obviously the p value is not less than the 0.00833 value. So we fail to reject the H naught, that is the H naught in this particular case is aspirin and acetaminophen behave in the same way. There is no reason for you to reject the null hypothesis. So similarly we can take aspirin and ibuprofen and do this similar study, okay, then we can take ibuprofen and acetaminophen and do the similar study and so on actually, okay. So it is very straightforward to do that. Do you understand how to do this problem? So basically what you do is, okay, what you do is, first step is to look at this equation, substitute all the data, and then get your statistic, compare it with the table statistic, and then you make you conclude in this particular case the drugs differ differently. Once you do that, you go into multiple comparisons for Kruskal-Wallis test, which makes use of this, okay. In that multiple comparison you calculate something called the Zij, that is comparing two cases I and J, okay, and then you calculate the probability from this, and after that there is something called Bonferroni corrected signal level, where alpha, if you take it as 0.05, 2m, m is given by k into k minus 1 by 2, where k, here we have 3 drugs, so k becomes 3, k minus 1 becomes 2. So if you put them together, what do you get? The Bonferroni corrected significance level is 0.00833, and the statistic you get 0.01044. So obviously this is much larger than this, there is no reason for you to reject the null hypothesis. Okay. Do you understand how this is done? So, this is useful for comparing more than 2 sets of data, whereas we used to use ANOVA, whereas in this particular situation when the data is ordinal or non-normal, then we can use this type of Krusvallis comparison, okay, Krusvallis test. Okay. Now, we looked at large number of approaches for non-parametric test. Okay. We looked at large number of approaches for non-parametric equivalent to your 2 sample and pair T test and one way ANOVA. We have all these rank based test. Okay. As you can see, many of them makes use of the rank. If you have a large data set, we rank them from in an ascending order and see how the ranks are. Okay. So, that is how this type of non-parametric tests are conducted, and then you have in some cases like Wilcoxon rank test, we have tables, you compare it with the tables, whereas Kruskal values you compare it with the chi-square. Okay. Okay. Now, there is another situation where you are talking where you are having non-normal type of distribution. Okay. In any normal, we if you are comparing 2 sets of data or multiple sets of data, we consider something called the homogeneity of variance. Okay. So, if that we need to check whether your data set has homogeneity of variance, that is very important. If they do not satisfy the homogeneity of variance, then we need to use some other type of test. Okay. So, for example, ANOVA requires the variances of different populations are equal. This can be determined by the following approach. How do you do that? We can compare graphically. There is something called box plot, I will show you, or we can compare variance, standard deviation. We can even do this statistical test like F test, right. Suppose we have 2 sets of samples, we look at the variance of set 1, the variance of set 2, divide one by another, that is called F test. And if we have many, then we perform something called ANOVA. Okay. But then there are other tests for checking the homogeneity of variances like Leven's test, Fligner-Killian test, Bartlett's test. So, all these tests are available. Let us look at 1 or 2, let us not spend too much time on remaining tests, because we can easily find out about the homogeneity of variance by using even these approaches also. Okay. What is a box plot? It is also called a box and whisker plot. Okay. This is a graphical depicting groups of numerical data through their quartiles. So, generally data is represented like this. So, this is called the quartile 1, this is called the quartile 3, and this is the median, or it is also called the second quartile. Okay. This is the maximum up to what the data goes up to, this is the minimum up to what the data goes up to. Sometimes if you have outliers which you do not consider in your quartile calculation, you put them as stars. Okay. So, this plot is very good because it tells you how the data is spread, the quartile 1, quartile 3, median, and what is the minimum value, what is the maximum value. So, it gives you nice picture, and if there are any outliers also we can mark it. So, if I have 2-3 data sets, we can draw this box and whisker plot and see how these rectangles are. Are the rectangles very big or the rectangles are very small? These are called whiskers. So, how the whiskers are spread and so on, that is called a box and whisker plot. Okay. So, for example, if this is your data and your box and whisker looks like this, obviously it is skewed to the right. Symmetric means it will be nice centered, it will be in the middle of the box, okay, both sides equal like this, whereas if it is skewed right, you will have it like this, if it is skewed left, you will have it like this. Okay. So, by looking at it, we can always say normality of the data. So, it is very good visual observation. This is called box and whisker plot. This particular pictures are taken from these reference actually. Okay. So, as you can see, when if it is skewed left, you will have lot of data. As you can see, the whisker very long, here the whisker is very short. If it is skewed right, you will have very long whisker on the right hand side, very short whisker on the left hand side. So, if it is symmetric, you will see both equal on both sides. Okay. So, it is a quick reference and this is called the box and whisker plot. Okay, then you have the Levin's test. So, what you do is you have a set of data, you calculate the residuals from the group means. So, if you have the group mean, then you subtract each one of the cell, you get the residual. So, once you get the residual, you perform an ANOVA on those residuals. Of course, you take the absolute value of the residuals. If the group variances are equal, then the average size of the residual should be the same across all groups. Do you understand? It is very simple. So, what you do is we take the mean and then we take the difference, take the absolute value. So, those are the that is called the residuals, absolute value, and then you perform an ANOVA. So, we can perform it for 2 data sets or 3 data sets ANOVA, and then we can show the H naught, whether it satisfies the H naught or not satisfies the H naught. So, it is very simple, that is called the Levin's test. Then we have the Fligner-Killeen test. What is this? This is also a non-parametric test for homogeneity of group variances based on ranks. Now, you have heard quite a lot about ranks, right? It is useful when the data is non-normal or when there are outliers. So, what you do is we calculate the absolute values of the residuals from the group medians, and then all these residuals are ranked. So, you may first calculate the absolute values, okay, then put them together and then calculate the ranks of each one of them, okay, and then you calculate the statistics called Fligner-Killeen, where this is summation of j is equal to 1 to k nj, okay, the size of the group j, aj bar minus a bar square by s square. Aj bar is the mean of the normalization value for the jth group, and a bar is the mean of all the normalization values, and s is the s square is the variance, and k is the number of groups, n is the size of the group. Okay, we can do this, okay, and after that we can check it using a chi-square distribution, one-tailed probability of the chi-square distribution, to see whether they follow the chi-square distribution, okay, as simple as this. You understand? So, you have the Levin's test, which is looking at the residuals from the average values and then perform an ANOVA, or we have the Fligner-Killeen test, where we are looking at the Fk, which is the statistic. This is based on the absolute values of the residuals, okay, and then you perform a chi-square distribution test to see whether the H naught is agreed or it is rejected. Okay. Then you have another test that is called the Bartlett's test for homogeneity of variance. Okay. So, you have here again a Bartlett's test statistics. It looks quite big, and this also makes use of the chi-square distribution. So, the equation looks big, where your n is the sample size of the ith group, k is the number of groups, n is the sample size of the ith group, k is the number of group, s is given like this, okay. S square is the variance, total variance, and Si square is the variance of the ith group, as you can see here, okay. The C here is given like in this formula. So, what you do is you calculate this test statistics, substituting the C here, substituting the S here, and then you use the chi-square distribution. So, what is the null hypothesis? That the all group variances are equal. It is rejected if p value is less than alpha, okay. And your chi-square distribution will B will come here, k is the number of groups. So, obviously k minus 1 is your degrees of freedom, okay. So, here the Bartlett's test, we have a statistics and then we apply chi-square distribution. In the Fligner-Killeen test, we have a statistics which makes use of residuals, then again we apply chi-square distribution. In the Levin's test, we calculate the residuals with respect to the average from each group, and then the data set containing residuals, we apply the one-way ANOVA. So, all these different types of tests help you to determine the homogeneity of variance, and it tells you whether the variances are equal or they are largely different. And of course, you have also have the box whisker plot, which pictorially depicts how the variances are of each set of groups of samples. Okay. So, we have been looking at non-parametric distribution where the data set could be non-normal, data set could be ordinal, the data set could have large differences in their variances. Okay. In such situations, what type of tests we can use? Equivalent to your t-test, 2 sample t-test, pair t-test, ANOVA, we have the different types of sign test, rank test, and so on actually. Okay. So, that sort of will complete the various types of tests. Okay. And let us look at some more distributions. We looked at Z distribution, then we looked at T distribution. Okay. Then we looked at chi-square distribution, F distribution. Let us look at one more distribution, that is called the beta distribution. Okay. This is also very useful distribution to talk about. Okay. Beta distribution is a random variable x is said to have a beta distribution with parameter. It has got 4 parameters, alpha, beta, A and B, if the probability density function follows this type of relation. Okay. So, it has got 4 parameters, alpha, beta, A and B. Okay. And x here, x will be lying between A and B, and alpha and beta are always greater than 0, you understand. So, this is how the relationship will look like. And alpha and beta are greater than 0. These are called gamma functions. I talked about long time back. So, gamma alpha is alpha minus 1 factorial, gamma beta will be beta minus 1 factorial, gamma alpha plus beta will be alpha plus beta minus 1 factorial. Okay. So, you have 4 parameters here, minimum, that is the minimum value, it can be anything, maximum, that is the maximum value, anything, alpha is greater than 0, beta is greater than 0, both are called the shape factors. So, you can have a special case, this is called standard beta distribution when alpha A is equal to 0 and B is equal to 1. So, if you substitute that in the previous equation, in this equation A is equal to 0 and B is equal to 1. Okay. What do you have? You have something like this, quite simple looking equations, okay, for x lying between 0 to 1. So, if it is 0 to 1, it will have a distribution, if it is not between these, it will be always 0 otherwise. So, for different values of alpha and beta, we can have different types of shapes, okay, as you can see here, beta distribution, okay, with the alpha of 0.5 and beta of 0.5. Beta distribution, that is probability density function, alpha of 0.5 and beta of 2. So, if you have both 2, 2, you get like this. So, if you have 2 and 0.5, you get like this. So, you can see that we can get a large number of shapes with these alpha and beta. So, this is very, very useful, especially for simulations and modeling. So, we can generate any type of function. As you can see, you can get maxima going down, you can get exponentially sort of falling down, you can have exponentially rising, you can have a linear rising. Okay. So, and then you can get bathtub type of curves. So, you can get any type of curve by manipulating your alpha and manipulating your beta. So, it is very useful for simulation purposes. So, if you want to generate any shape, we take this beta distribution function, put A and B as 0 and 1 respectively, and we can use whatever alpha and beta we want to use to achieve this shape. Okay. Let us go forward. So, it can take a wide variety of shapes, it can look like triangular, uniform, exponential, normal, log normal, gamma. So, it is fantastic actually, used extensively in project planning, controls, okay, growth curves in your bacterial systems, like as you can see, we can get different types of growth curves, okay, different types of growth patterns, you know, using modifying your alpha and beta. So, the mean of this will be like this, A plus B minus A alpha by alpha plus B. So, if A is 0, B is 1, what happens? You will get alpha divided by alpha plus b. Your standard deviation is given like this. So, if b is 1, this will go away. So, your standard deviation will be square root of alpha b divided by alpha plus b square root of alpha plus beta plus 1. Okay. So, there is something called cumulative distribution function. So, you just need to integrate between 0 to x, okay, of the beta distribution, okay, and it is given like this. B is your beta function, okay. Beta function is nothing but this is your beta function, sorry, this is your beta function. So, you can integrate that to get your cumulative distribution function. So, for example, if your probability looks like this, sorry, probability density function looks like this, your cumulative will look like this. If your probability density function will look like this, cumulative will keep on increasing. Cumulative generally will keep on increasing. So, if your probability density function looks like this, for 2 and 2, your cumulative will go like this. If your probability density function looks like this, your cumulative will go like that. Okay. So, this equation is also useful because it gives you an idea about the cumulative density function. Okay. So, let us look at an example. Time necessary to complete any particular activity once it has been started follows a beta distribution. Suppose A is the optimistic time, it is given in 2 days, B is the pessimistic time given 5, alpha is equal to 2, beta is equal to 3, then the mean will be 3.2. That means on an average it will take you 3.2 days to complete the task. Now, for these values of alpha and beta, the probability density function of x is a simple polynomial, because if you substitute the cumulative distribution function like this, okay. So, we put your alpha as 2, beta as 3, okay, alpha as 2, beta as 3, and then A as 2, B as 5. So, you substitute this into the equation and you integrate them, you end up with a probability of 0.407. So, the probability of completing the task at most 3 days, that means maximum of 3 days, is given as a probability of 0.47. Okay. And you also in your Excel we have this beta dist, okay, which gives you x, alpha, beta, a, b. Okay. So, let me look at it. Excel. So, we have the Excel function which is given by beta dist equal to beta dist, and you want to calculate at say it is given as x, alpha, beta, a, b. So, in your case alpha and beta is 2 and 3 respectively, a and b is 2 and 5 respectively. So, if you want to finish it in 3 days, okay, what happens? 2, 5, sorry, if you want to finish it in 3 days, as here at most 3 days, what should it be there? So, we need to put the values, sorry, 3, 2, 3, because alpha is 2, beta is 3, then A is 2, that is the optimistic time, then the pessimistic time is 5. So, you get 0.407. So, the probability of finishing it in at most in 3 days is 0.407. That is same as what is got by integrating this cumulative distribution function. So, we can use the Excel to do the same thing, and Excel has this beta dist command. You want to know the probability at any value of x, and you know the alpha, you know the beta, you know these A and you know the B. So, it gives you at 0.407. Okay. So, we will continue on this distribution in the next class also. Thank you very much for your time.